You want to test whether you can hear me at the exit sign? One more time? Sounds good.
Thank you for coming. Appreciate it.
Sure.
Haven't seen you in a while.
It's been a while.
Yeah. Well, you'll have a big audience outside. There's a couple of meetings that were scheduled over this, unfortunately. But, the federal
Good afternoon. I'm Stephanie Parent, and I'm introducing today's Chairs Seminar speaker. Before we begin, I would like to encourage everyone watching on the webcast to send their email questions during the broadcast for our question and answer session later to the email address auditorium@calipa.ca.gov. And we'll hold questions until after the presentation is finished. It's my pleasure to introduce to you today Dr. William W. Nazaroff. Dr. Nazaroff is the Daniel Telep Distinguished Professor and Vice Chair for Academic Affairs in the Civil and Environmental Engineering Department at UC Berkeley. Professor Nazaroff's research group focuses on the physical science and engineering aspects of air pollution exposure with a special emphasis on indoor environments. At present, Dr. Nazaroff serves as Vice President-elect of the American Association for Aerosol Research, as co-editor of Indoor Air, and as Vice President of the Academy of Fellows of the International Society of Indoor Air Quality and Climate. Professor Nazaroff joined the Berkeley faculty 2 decades ago after receiving his education in physics, electrical engineering, and computer science at UC Berkeley, and earning his PhD in environmental engineering science from Caltech. Dr. Nazaroff served on ARB's research screening committee from 2000 to 2002. Dr. Nazaroff is author and co-author of over 120 research articles published in archival journals and co-author with L. Alvarez Cohen of the textbook Environmental Engineering Science, published by Wiley in 2001. Today's presentation is based on research funded by the Air Resources Board. Please join me in welcoming Dr. William W. Nazaroff.
Thanks. Thank you, Stephanie, and good afternoon, everybody here, and good morning, night, whatever it is, for those of you who are listening on the web. It'll be my pleasure today to share with you some of what we've learned over the past few years studying the occurrence and the reasons for those occurrences and the significance of ultrafine particles with respect to human exposure occurring in indoor environments, and in 2 particular indoor environments, classrooms and residences. So before I launch into the presentation, let me just take care of a little bit of business, acknowledging that a large part of the research reported here was conducted by 2 PhD students, Seema Bangar and Nassim Mullen. We also worked in cooperation with Suzanne Herring and Nathan Kreisberg from Aerosol Dynamics. As Stephanie mentioned, the funding for this work was provided by the Air Resources Board, and you can read the standard disclaimer that we include every time we talk about this work. So a little bit of background as we launch into this subject. First, there is emerging evidence from laboratory studies and also from field epidemiological investigations suggesting that there are reasons to be concerned about human exposure to ultrafine particles because of health risks that may be posed. We have quite a bit of evidence about the prevalence of these particles and the factors that lead to their presence in the ambient atmosphere. 2 major sources are emissions from motor vehicles, and so concentrations on and near roadways are of large concern. And then there is also the issue of regional nucleation events, which seem to occur wherever scientists look for them on an occasional basis and produce a broader swath of new ultrafine particles. It's important also to recognize that our current regulatory and monitoring system emphasizing PM 2.5 really doesn't tell us very much about ultrafine particle levels and exposure, and the studies that have looked at both of these indicate that there may actually be anti-correlated rather than positively correlated. Because people spend most of their time indoors, even if the sources are primarily these regional nucleation events and motor vehicle emissions, a large fraction of human exposure would occur within buildings, or a significant fraction in any case. And yet little is known about the levels of ultrafine particles within buildings and the factors that influence them. And not on the screen, but also of importance, are that there are sources of ultrafine particles that emit directly into the indoor environment. So our objective was to advance the knowledge that's available regarding ultrafine levels, ultrafine particle levels, and the associated exposures of humans in 2 classes of indoor environments, classrooms and houses. And more specifically, our goals then were to characterize the ultrafine particle levels in a sample of houses and classrooms, to characterize the factors that influence those levels, to quantify the exposure that occurs to the occupants of those households and the students that were in the classrooms that we monitored, and to apportion the exposure to major source categories. In particular, we wanted to understand to what extent were exposures attributable to particles originating outdoors versus those originating from indoor sources. So the approach that was undertaken was first to assemble an instrumentation package. We used commercially available instruments for all of our monitoring. We did real-time measurement of ultrafine particles and a suite of additional pollutants that may be associated with ultrafine particle formation. We also made measurements of the operating conditions of the buildings using temperature and proximity sensors coupled to data loggers. We also collected information using questionnaires and direct observation in the classrooms to understand patterns of occupancy and the potential use of indoor sources of ultrafine particle emitting processes. The field monitoring campaign entailed making measurements in a total of 7 houses over a span of time that was approximately 1 week per house, and 6 classrooms. The 6 classrooms were situated in 4 separate schools. The field monitoring campaign was divided into 2 parts at each site. One part was observational monitoring, where the goal was just to have the space used as it normally was and to measure the real-time concentrations indoors and outdoors of the species we were observing, plus the configuration of the room or the building. And then we also did some manipulation experiments targeted at elucidating governing processes at each of the sites. And we spent the last year of the project focused on interpretive analysis of the data and on reporting. So a little bit more about this field monitoring approach. At each of the sites, we aimed to conduct real-time monitoring over a continuous period around the clock with these instruments for at least 3 days. At some sites, we had interruptions because of instrumentation or other difficulties, and so we would have a gap of a few days and then continue a second period. With the manipulation experiments, we typically had full control of the space, and the spaces were unoccupied during these times. We measured air exchange rates of the spaces that we studied using deliberate release of carbon dioxide as a tracer gas and measuring its decay. And then we conducted experiments to characterize the penetration and persistence of particles from outdoors, and also to quantify the release and decay of particles from representative indoor sources. A quite important background piece of information that facilitated this study was the development several years ago of the water-based condensation particle counter. So the condensation particle counter or condensation nucleus counter is a device that's been around for a very long time, perhaps a century now, for measuring airborne particles. Historically, an alcohol such as butanol was used to cause the very small particles to grow so that they could be detected. Butanol is a difficult substance to work with in occupied spaces because of health concerns and annoyance that is associated with it. And so there wasn't a lot of monitoring that had been done in indoor environments, especially ordinarily occupied indoor environments, using this technology. But with a water-based condensation particle counter, we're now able to very safely use this device in ordinarily occupied spaces. And the instrument then measures number concentration in real time. We acquired data with 1-minute time resolution. The number concentration of particles from the line being sampled with a minimum size cut with this particular instrument at about 5 nanometers or 6 nanometers. And we use the particle number concentration, which was what we're actually measuring as a proxy for ultrafine particles. Those are very highly associated. We did not make size-resolved measurements of particle concentrations in this study. So this slide summarizes the real-time monitoring instruments. We had a total of 3 instrument packages. There were 2 sort of complete packages with not only the particle number concentration instrument, but the copollutant monitors, 1 indoors and 1 deployed outdoors. And then we had a 3rd condensation particle counter that was deployed at a 2nd indoor location. We measured carbon dioxide, carbon monoxide levels, the temperature, the relative humidity, and then continuously ozone and nitric oxide, both indoors and outdoors. This slide illustrates or depicts the instrumentation package. So the instruments were placed in these black cases with a mast mounted on the top so that the air samples were drawn from effectively the breathing height of a standing individual, about 1.5 meters above the ground. And the configuration of these instruments inside the black case was designed to ensure that the instruments could be deployed in a situation with children around and left to operate unattended without them being disturbed, and that worked with a good degree of success. We did find in the schools that because of our interest in also having strong data about occupancy and configuration of the school, like window and door openings as a function of time, that it proved to be more effective to have one of our researchers continuously present in the classroom whenever it was occupied to acquire the data that way, and that ensured then that the instruments were not also not interfered with. Briefly, we did an extensive quality assurance and quality control program as a part of this research, and I just want to show a few of the elements of that. So the pollutant monitors other than the ultrafine particle instrument were calibrated roughly monthly, either against a more primary instrument standard in the laboratory, a reference instrument, or against gas standards. The WCPC, the particle concentration instruments, had their flow rates checked routinely in the field at each site. And at each of the sites, we deployed each of the instrument packages for several hours in a side-by-side sampling mode so that we could adjust the instrument responses so that they matched one another as closely as possible, in addition to the calibration against primary standards. And you can see in the figure that's displayed on the lower left a sample of the side-by-side monitoring results. So these are minute-by-minute measurements of two of the WCPCs measuring continuously the indoor particle levels at one of the house sites. A very high correlation coefficient, low intercept, slope of 1. And the average slope of the side-by-side monitoring results with QME, which is the label for the instrument, QME-A, as the reference instrument is shown in the table on the right. So it was 5% roughly is the average deviation in side-by-side comparisons. I want to next turn to the more kind of detailed investigation that we undertook in houses, and then later I'll come back to talk about schools. So our sample of houses was a convenience sample. It wasn't intended to be statistically representative. All of the houses that we monitored were from the East Bay Area of Northern California. I'll give you a little more detail on where we monitored in a moment. We did have some source-oriented criteria that were factored in so that the overall goal in the selection of the houses was not only to have them be typical in some sense, they were all single-family dwellings, but because of the source-oriented criteria, we were probably tilted a bit high relative to central tendency in average concentrations that might be encountered in indoor environments. But we were also careful not to pick houses that would be extremely high. So we didn't include houses where there was extraordinary candle use, for example, or houses where there were smokers. There were no smoking households in this study. The 5 of the houses that we monitored were in the city of Oakland, and most of these were located in the urban core residential areas of Oakland in the flats. One house, and you can see from the ages or the years built that these are relatively older houses compared to the average of the California stock, but not so old relative to the inner city of our older cities in the state. Livermore and Emeryville were the communities of the 2 other houses we monitored. These were more modern households. The number of residents that were included in these 7 houses totaled 21. There were just coincidentally 7 adult males, 7 adult females, and 7 children. And we didn't plan this, but it turned out that all 7 children were males. So we have no data on little girls' exposure to ultrafine particles, I'm sorry to say. We did pay attention to how close we were to roadways, and it was one of the criteria that a few of the houses should be on the order of 100 meters or less from a major roadway. I'll show you some data later to suggest that this didn't emerge as a dominant factor influencing the concentrations that we obtained. But you can see in this figure the houses that we monitored relative to the location of major roadways, and in particular H3 and H4 were right next to heavily traveled roadways in Oakland. So now I want to just walk you through. In the end, the nature of the study might be best considered as 13 case studies. Every one of the sites that we measured or monitored had their own characteristics, their own attributes that required thinking about them somewhat differently than the others. And I don't have time in this forum, and it would be tedious anyway to do it, to go through all 13 of the sites. So what I'd like to do is to present to you some details to give you a flavor for how we approached this and what we learned from one house and from one school, and then summarize overall the data that we obtained. So the house that I've chosen to report to you on here is H6. The site plan is shown. It's a 2-story house. We occupied by 3 adults. The monitoring outdoors took place immediately adjacent to the outside of the house. We deployed the other 2 instrument packages on the 2 separate floors. You can see them depicted here or enclosed in the red squares. This house, again, was located in Emeryville. It's a relatively modern house built just over a decade ago. Natural gas cooking appliances, but without a continuous gas pilot light, as is common for modern appliances. They did use candles once during the monitoring period. We measured the air exchange rate by tracer decay on 3 instances during our study and found values in the range of 0.8 to 0.9 per hour, which is not atypical for residential buildings in California. The time series of particle number concentration for the 3 monitors is depicted in this slide from observational monitoring. So just to orient you, the horizontal axis is time. In hours, it extends about just over 72 hours at the site, so a little bit over 3 days. The vertical axis is the particle number concentration measured in the number of particles per cubic centimeter. And the upper frame reports the outdoor measurements. The lower 2 frames report the indoor measurements at the 2 monitoring sites indoors, one downstairs and one upstairs. I would call your attention to the fact that the upper 2 frames have the same vertical scale, but the lowest frame has a somewhat different scale by a factor of 2 or 3, because I needed to do that to keep the peaks within the frame. And what is observed is not atypical on a linear scale. What we found at every site was that there were periods of time when the indoor concentration more or less tracked the outdoor concentration, but on a linear scale you can't see that in these figures, because the dominant feature of what's going on indoors are these episodes of very high emissions that take place, leading to quite exaggerated elevated indoor concentrations, followed by subsequent periods of decay. And I've placed letter labels on the peaks that were observed at this site. So there were, depending on how one counts them, I guess the way that I've scaled them here, there are 9 labeled peaks. E you might call a double peak. Based on the questionnaire data and the additional information that we collected, we are fairly confident that most of these peaks were associated with cooking activities in the house. Peak C was a candle-related activity, and emissions there we believe were associated with the use of candles. I mentioned that we monitored copollutant data, and those copollutant data help somewhat to reinforce the evidence that we have about the nature of the sources. So here I have plotted that same indoor monitoring, concentration monitoring trace as the lower frame, and aligned with it as the upper frame, the indoor concentration of nitric oxide. So when natural gas is used as a combustion fuel for cooking, nitric oxide and nitrogen dioxide can be emitted, and that can cause an elevation of the indoor concentrations. And you see that we believe from the activity data noted down at the bottom that A, B, D, E, F, G, I, and J were all from cooking-related activities. You can see from the nitric oxide data that the most of these peaks, most of the particle peaks, have associated with them, but not all, have associated with them excursions in nitric oxide levels above the baseline as well. And in some cases, like in D, the excursion is pretty rather pronounced, 200 parts per billion rise above the baseline. In H, the nitric oxide level seems to rise, although not in the same fashion as it does in the other cases. We don't have evidence then that a gas combustion appliance was used, but rather that a toaster oven was being used, and that might have been the source of the particle levels. And it's possible that the elevated nitric oxide level is actually coming in from outdoors during that interval. And then you note in case C, where the diary suggests that candle use was the cause or associated with the ultrafine particle emissions, there is not a nitric oxide signal associated with that peak. And candles are not believed to be a significant source of NO, so that's sort of a consistent bit of evidence. Important information emerged in this study. It actually was more important than we anticipated when we wrote the proposal about the interplay between occupancy, the levels of ultrafine particles, and of course, occupancy is essential for exposure to occur. It's not so terribly interesting what the levels are inside a house when there's nobody in the house. So we collected data from questionnaires recorded daily by the occupants of when they were at home awake, when they were at home asleep, and when they were away from home. And this figure is just intended to illustrate the nature of those data for the 3 occupants at this site. One other quite important bit of information, there's much more detail in this table than I want to go over, but an important bit of information that emerged from this study was knowledge about the penetration and persistence of ultrafine particles originating outdoors and how those influence the indoor levels. And so we referred to the ratio of, okay, so the particle levels that are present within the building could be thought about as having 2 dominant components. One is the particles that originated because they were emitted indoors, and the other is the particles that originated outdoors and came in with the ventilation air. Those particles that originated outdoors don't exist indoors at the same level that they do outdoors, because they may be lost as air leaks into the building, they may be lost by deposition onto indoor surfaces. So the indoor proportion of outdoor particles is something that we're interested in knowing, because that would allow us to connect monitoring or modeling of ambient concentrations to the expectation of what would be present indoors in the absence of indoor sources. That parameter we label F in this study, and so F1 is the indoor proportion of outdoor particles at monitoring site 1 indoors, and F2 is that proportion at monitoring station 2. And we found that we could use periods of time that were evidently quiescent from the time trace, the time series record of ultrafine particle levels indoors. That is, evidently not influenced by indoor emission sources, because most of these emission sources had this spiky character. So we could eliminate those periods, take the periods of time principally when occupants were away from home, and then take the ratio of the measured indoor concentration to the measured outdoor concentration during that period as a means of evaluating or estimating this parameter F. And that's what this table reports. The 5 periods at house site H6, where we believe the indoor concentrations are only a result of outdoor sources. The duration of those periods is indicated in the left-hand column, reference to the start of our monitoring period. And what I want you to note particularly is these F1 and F2 columns, and the bottom line, the overall average, the time-weighted average, 0.44 at F1, 0.51 at F2, meaning that about half of whatever the ultrafine particle levels were outdoors were still present as a contribution to the indoor level at this particular house. We also analyzed the episodic events where the particle levels suddenly rose indoors because of an indoor activity and aimed to quantify two parameters from each of these events. One is an emission source strength. What's the total number of particles that were emitted by this event, adding to the indoor level? And the second, a decay constant associated with the return of the elevated concentration back toward the baseline. So here I have summarized in this table, the decay constant is K plus A. That includes air exchange and deposition onto indoor surfaces and any other loss mechanism. You can see that these emission activities have decay constants that range from a little over 1 to a bit over 3 per hour. And then the other parameter is sigma, the total number emissions of ultrafine particles effectively associated with these events. And you can see that these numbers range from 5 to something in the mid-50s in units of trillion particles, 10 to the 12th particles. Now, if something emitted less than about 1 trillion particles, we couldn't see it against the fluctuating baseline concentrations contributed by outdoor levels. So our threshold for detection is about 1 trillion particles. That's what it takes to elevate the indoor concentration by enough so that we can clearly see it. And there are several of these events that produce high levels, and we saw these at each site. This is way too detailed, and I'm sorry I didn't have time to produce something that was more appropriate for an oral presentation, but I did want to give you a sense that the last important stage that was undertaken in our work, and I'll report the summary evidence more completely in a moment, was to determine exposures for each of the occupants to ultrafine particles during the time of our observational monitoring while they were at home. So this doesn't include whatever exposure that may have occurred when they were not at home. We don't know what that would have been. And we are able, through interpreting the data, to apportion the cause of those exposures to the penetration of particles from outdoors and the emissions of particles from all of these indoor activities. And we do that for each of the occupants separately. So in this particular case, the three columns, R1, R2, and R3, refer to resident 1, resident 2, and resident 3. And the exposures at this house during the time that we monitored for these occupants range from 23 to 29% attributable to particles from outdoor origin, 72 to 76% from, you can see down here where the hand is. Is that my, oh, that was a mistake. Sorry. I'm not going to try to do that anymore. I will just talk my way through this. The 72 to 76% attributable to these episodic indoor sources, and 1 or 2% that we couldn't apportion. So now some summary information. First question is, to what extent are the indoor particles that we monitor correlated with the particles that we measure outdoors? It'd be great if they're very strongly correlated from the standpoint of exposure, because then monitoring outdoors, you can make some assessment of what's going on indoors. Well, the correlations are not particularly impressive. And the underlying reason is because of the importance of indoor sources in contributing to emissions. So the R-squared values are 0.26, 0.49. The overall average concentrations indoors turn out to be about the same as the overall average concentrations outdoors. For the 7 houses that we monitored, the average was close to 15,000 particles per cubic centimeter, both indoors and outdoors. But the indoor concentration is not caused just by the outdoor concentration. It's a coincidence that the penetration of particles from outdoors and their persistence indoors, plus the contribution from indoor emissions, sums up to about the same as we monitored outdoors. And quite importantly, from an exposure point of view, is the fact that the indoor particle levels are systematically and substantially higher when people are awake at home than when they're asleep at home or when they're away. Now, you know, in hindsight, that's not surprising, but we didn't know this coming in. And the scale of the numbers, I think, is pretty dramatic. So here on the right-hand side, I have the overall averages for the 7 households summarized. When people are awake at home during our monitoring period, the average outside concentration was 17,000 particles per cubic centimeter, and the average indoor concentration was about twice that, 33 to 35,000. When people were asleep at home, the average outdoor concentrations were lower. They tended to be lower overnight than they were during the daytime. The average indoor concentrations, though, didn't have big contributions from indoor sources, and so they were even lower still, 5,000 per cubic centimeter. And when people were away from home, the outside levels were pretty similar to when they were awake at home, 17,000, but the inside levels were principally just due to the penetration and persistence of those outdoor particles. And so almost a factor of 4 lower during the daytime when people are not at home inside than during the daytime when they are at home. I've talked now about what this indoor proportion of outdoor particles means, and here's a summary of the results from all 7 of the house sites. If you just focus on the bottom line, the main monitor that we put in a central location in each house, the average penetration and persistence number was 0.38, and the median was 0.44. You can see from the column of F1 values that they range from 0.1 to 0.5 across the 7 houses that we studied. Qualitative summary of the sources that we observed to be present and significant indoors. Whenever gas cooking took place, it was an important source. We found that gas clothes drying, which had been reported previously as a source of ultrafine particles, was only a source at 1 of 4 houses where a gas dryer was used. We found that the furnace was sometimes a source, but not always. We found that electric cooking was also a source, not as strong as gas cooking. So it's not just combustion that leads to the emission of ultrafine particles indoors, but high temperature processes seems to as well. The use of a toaster oven was a source at several houses. The use of candles was a source, and ironing clothes was also a source. I'll say a bit more about the terpene issue when we get to schools. We, overall, in terms of summarizing the emissions from these sources quantitatively, we identified 59 peak events that occurred in the roughly 20 to 25 monitoring days, so about 2.5 events per household per day that we monitored. And when we could ascribe the emissions to one activity rather than having 2 activities occur simultaneously, confounding our apportionment. This is a summary of what the emissions characteristics look like. So you can see in terms of strength that the gas stove, the central furnace, the use of candles had sigma values that were 25 to 40 trillion particles. Electric stove cooking was on a similar scale, but somewhat lower in magnitude. And then other things like the steam iron or the clothes dryer, when we could detect them, were about an order of magnitude reduced. And all of these activities had decay coefficients that were about the same on average, 1.5 to 2.2 or so, 1.3 to 2.2, maybe 1.1 per hour, but varying over a pretty narrow range. The apportionment of exposures, when summarized for all 21 occupants, look like this. So the measure here is the daily average exposure rate, where exposure is the product of the average concentration during occupancy times the duration of occupancy. So the units are this weird combination of concentration units, number of particles per cubic centimeter, thousands of particles per cubic centimeter, multiplied by duration in hours per day. So it's thousands of particles per cubic centimeter, hours per day of exposure. as a daily contribution from the time people spend indoors. And you can see that the highest numbers occurred at site H3. They were 650 to 700 in these units. The next highest were at H1, maybe 400, and then the rest of them were somewhat lower than that. The blue part of this figure illustrates the contribution from outdoor particles, the red from indoor episodic sources. At 2 of the houses, there were continuous pilot lights on the gas combustion appliances, and those contributed significantly to exposure, as depicted by the green section of the bars. The overall average for the 21 people was about 300 in these units, 300,000 per cubic centimeter hours per day, with 29% of that attributable to outdoor sources, 61% associated with the episodic releases indoors, 8% was the average over all 7 sites from gas pilots. I guess one other point to note is that at least for this study, there was more house-to-house variability than there was variability among the occupants within a house. I think in the interest of time, I will skip this next slide and let me move on and talk about the part of our work that was done in schools. So again, with schools, this was a convenience sample. We had to find schools where we had the cooperation of the administration and the teachers. And so we did all of our work in elementary schools in the urban portion of the East Bay Area. And we worked with a couple of different school districts and in total monitored at 4 school sites, 6 classrooms. So the students range from 1st grade through 5th grade. We didn't do any monitoring in portable classrooms, so these were all built classrooms on site, and they varied from almost isolated or classrooms that belong to a pod that might have just a couple of classrooms in a building to classrooms that were part of a larger ensemble. They also varied in the degree to which they were mechanically versus naturally ventilated. So in particular, S1 was a quite old classroom that didn't have any mechanical ventilation. The teacher used doors and windows to control the temperature. And the S4 was also a purely naturally ventilated space. The other 4 had mechanical ventilation of some sort. We also took a look at proximity to roadways, and I'll show a summary for all of our outdoor monitoring, what we observed in the average outdoor levels in relation to the in relation to the distance from the roadway in a bit. As I did for the case with houses, I want to walk you through an investigation at one school site and then provide a summary. So I'll use S1 as the particular site. And the first important thing that I want to note that's a strong qualitative difference between what we observed in the houses we monitored and what we observed in the schools is that in the houses, indoor sources were quite important in the overall picture. In schools, really not nearly so much. The sources were infrequent, contributed a small fraction of the total indoor particle loading. Most of the particle loading in schools came, again, from our monitoring, came from outdoors. So this figure illustrates the outdoor concentration as a function of time. You can see in the upper frame, these outdoor concentrations are higher in the middle of the day during this period in June than they are overnight. And the indoor levels in this classroom, which was indoor 1 that we're monitoring, were sort of follow the outdoor picture. So the levels rise during the middle of the day and then sag overnight. In this particular case, indoor 2 was monitored in a hallway outside of the classroom, and there was some more traffic there, foot traffic, and also I think a higher overall average ventilation condition. We have occupancy data here, not from questionnaires, but from our direct observation. So for every day that we monitored, one of our staff was inside the classroom, keeping a record minute by minute of the configuration of the classroom, whether doors and windows are open, activities that might have led to release of ultrafine particles and how many students and adults were present in the classroom at that moment. So this is an illustration of the time trace of occupancy. As with houses, we found a correlation between occupancy and indoor particle levels. That is, when the classrooms were occupied, the indoor particle levels tended to be higher than when the classrooms were not occupied. But in contrast to the case in houses, where indoor sources were a major reason for that, in schoolrooms, the major reason is tied to ventilation. So when the classrooms are occupied, the ventilation rate is higher. When the ventilation rate is higher, there is a higher penetration and persistence on average of the outdoor particles than when the ventilation rate is lower. And here you see that just look at the figure on the left. On a time average basis at school site S1, the outdoor particle concentration was 26,000 particles per cubic centimeter when children were present, 16,000 particles per cubic centimeter indoors. When the classroom was vacant, the outdoor level dropped by about a little bit more than a factor of 2. The indoor level dropped even more. And I'll come back to this in association with this parameter F momentarily. I said that indoor sources in general weren't terribly important in schools. We did see a few episodes. So the one that occurred at S1 was associated with cooking of pancakes. I don't know why. They were cooking pancakes on a griddle in the classroom one morning, and the particle levels indoors shot up to 300,000 per cubic centimeter, lasted for 5 or 10 minutes, and then that was the end of that episode. This one small excursion contributed 5 to 10% over the 3-day period of the exposure of the kids and the teachers that occurred within this classroom. One of the things that we set out to investigate was the role that terpene ozone chemistry might play in contributing to ultrafine particles indoors. We didn't see a lot of evidence of this. In schools, the interesting feature is that sometimes a terpene-based cleaner was used to mop by the janitors, but that tended to be done late in the day after the kids had left. And so we replicated this in a controlled experiment, a manipulation experiment, using the mopping liquids that were provided by the janitorial or the custodial personnel to carry out, while the classroom was vacant, a floor mopping exercise. And in the upper figure, you can see what happened with the particle levels in this case. They were at, the indoor and outdoor levels were tracing pretty close to one another, 10 or 15,000 particles per cubic centimeter. Mopping was conducted. Even though the indoor ozone level was only 10 to 20 parts per billion, the indoor particle level, because of terpene ozone chemistry forming ultrafine particles, jumped up to 120,000 per cubic centimeter, and that the elevated level persisted for some hours afterwards before returning back to the baseline. The summary of our story for classrooms looks something like this. So on the left, I have plotted the time average concentration outdoors, that's the striped bar, and indoors, that's the solid shade bar, when students are present in the classroom. And on the right-hand side, a similar plot, the time average values, when the classroom is vacant. Systematically, the levels at almost every site, save for S5 and S6, were higher when the classroom was occupied outdoors than when it was vacant. And they were also higher indoors in every case when the classroom was occupied compared to when it was vacant. So on the right, I have a summary of the overall averages. The average outdoor concentration at these sites during occupied periods, 18,000 particles per cubic centimeter. When the classroom was unoccupied, about 12,000 particles per cubic centimeter. Indoors, when the classroom's occupied, about 11,000 particles per cubic centimeter, higher than homes when people are asleep, lower than homes when people are awake and at home. And indoors, the level is down considerably when the classroom is vacant by somewhat over a factor of 2. An important feature, as I've mentioned, is that when the classrooms are occupied, the classrooms tend to be better ventilated. And when the classrooms are better ventilated, especially if that involves opening the doors and the windows, there's more ready exchange of or introduction of particles from outdoors into that environment. and less time for particles to decay or deposit onto indoor surfaces. And so the indoor proportion of outdoor particles is elevated during times of occupancy compared to times when the classroom is vacant. And that is summarized in a way in this table where I report for each of the sites where there was some monitoring time where the classroom was closed. The air ventilation was off and the doors were closed. The F1 value for the 4 sites where this occurred averaged 0.38. When the classroom was open, the doors were open and/or the mechanical ventilation was on, the indoor to outdoor concentration ratio was considerably higher, averaging 0.6 across these sites. From an exposure point of view, the exposures that occurred daily, bless you, the exposures that occurred daily to the students and the teachers in the classrooms are summarized in this figure. The overall average for the 6 classrooms that we monitored in these same units that I've referred to before were 50 for students and 80 for teachers. That compares, remember, with the number 300 for the value that was occurring for the occupants of the households. The principal reason for the lower number for students as compared to teachers is because teachers are in the classrooms for more hours per day than the students are. And the principal reason that a dominant reason why these levels are lower in classrooms than they are in homes is because, again, of occupancy duration. Students were present on average for 3 to 4 hours a day inside the classroom for the monitoring period of this study, and they were present at home for typically 16 hours a day. The average levels in the houses were also a little bit higher than the average levels inside the classrooms, but that was a smaller contributor to the difference in these results. Now, one of the things, because indoor sources were not found to be so terribly important in the school sites, outdoor concentrations are actually a decent predictor of exposures that occur for children within the space of our study. However, it's quite important to monitor during the time when students are present in school rather than to take the overall 24-hour average concentration. So the figure on the left attempts to correlate the daily average exposures that we've calculated for the students and teachers in these classrooms against the 24-hour average particle number concentration. And the correlations are okay, but you see a very sort of severe shift from a zero intercept. We do a lot better, both in terms of the strength of the correlation and in the rationality of the result, when we compare time average concentrations during the period when students were present in the school or when the teachers were present in the school against their exposure, and that's what's shown on the right-hand side. So there the R-squared values, 0.9, 0.83, pretty good basis for estimating what exposures would be like to the extent that our set of classrooms is at all representative. I mentioned that we know from a lot of other work that being close to a heavily traveled roadway correlates with amplified time average particle number concentrations. Now, in this case, we can't separate, because of the nature of our study, time and space. We didn't measure at the same time sites at different distances away from roadways. And so if we just look crudely at the time average concentrations we measured outdoors plotted against distance from the nearest freeway, you can see a relationship, but it's a quite weak relationship. And these are only the outdoor particle concentrations, so it's not influenced by the indoor dynamics, either by indoor sources and so forth. And this isn't to denigrate the significance of roadways as an important source, but just to point out that it's more than distance from a roadway that influences the outcome. So to summarize, the key findings in our study, there are probably 4 main points to take away from this. First, the particle number concentrations, ultrafine particle levels in classrooms and in houses, in both cases, are quite a bit higher when those spaces are occupied than when they're vacant. And this should give us pause for thinking about doing 24-hour average monitoring as a basis for understanding what's going on with exposures indoors. We really need to know what levels are when people are present in those environments, not just for ultrafine particles, but for a broader suite of pollutants. Second, indoor emission sources we found to be important in houses, contributing quite a bit to exposure, and not so important in schools. Third, the daily average particle number exposures per person are much higher in houses, about 300 in these units of 1,000 per cubic centimeter hour per day, than in schools, for which we found for students about 6 times less and for teachers about 4 times less. Partly that's due to duration. That's the bigger factor of occupancy, but also influencing this is the difference in average levels. And then we found that the indoor proportion of outdoor particles tended to be higher in classrooms because they have higher ventilation rates on average than in houses. 0.57 is the average ratio we observe for classrooms, 0.38 for houses. Important caveats: this is a very small sample of buildings. The monitoring was done on just a few days per site. The buildings were not selected to be statistically representative, and we only monitored in one area in California. So one ought to apply caution in trying to infer some general truths from the observations of these studies. I think the study results themselves are valid within the space of the study, and they may provide important clues about what's going on more generally. But we can't conclude what's going on more generally based on this limited evidence. So recommendations then for what might be done beyond this. I think there's enough evidence about the health significance of ultrafine particles to warrant continued attention to better understanding exposure. And I think this study that I'm reporting here provides a nice platform for a more efficient but maybe broader investigation in additional classrooms and houses. I think it's especially important to be attentive to the spatial and temporal dimensions of exposure. Ultrafine particles are going to be a difficult issue for us to deal with as a air pollution, air quality control community, in part because of the high temporal and spatial variability. So whereas for ozone, for example, you put up a monitoring station in a region, you get pretty good characterization of what the ozone level looks like regionally. You can't do that with ultrafine particles. They're much sharper spatial gradients, and the importance of indoor sources and near-field sources to people mean we have to be attentive to this. I think we need much more careful attention to the near-field effects of motor vehicle emissions on ultrafine particle exposures. Some of this is taking place with on-roadway studies. I know Dane has been involved in such investigations. And I know some work has gone on in looking at what happens in the near vicinity within buildings. There was one particular study conducted by UCLA that looked at this in Southern California. Those provide a nice platform, but it's an area that can't be addressed casually and I think needs to be embraced more aggressively. And then, although I realize that the question of whether this lies within ARB's mandate or not is not so clear, the significance of cooking as a potential source of exposure to ultrafine particles, I think, merits some careful investigation, because my expectation is that a lot of our exposure is attributable to this one class of activity, and if we don't sort out, even if we're going to end up focusing on other sources from a regulatory point of view, if we don't sort out the contribution to exposure from this source, there's going to be a lot of confounding. So that reaches the end of my prepared remarks. I'm happy to take questions, and thank you for your attention.
Thank you, Professor Nazaroff. First, I'd like to remind people watching on the webcast that you can email any questions to auditorium@calepa.ca.gov. And first, I'll start with a question that was emailed from the internet. Do you know of any health-based guidelines or standards for desired PN levels in residences?
No. I'm sorry, I'm usually not so much at a loss for words, but that's just not, there's no good basis for that yet. We're too early in understanding health effects.
I'll take a couple questions from the audience.
Can you go back to the slides summary for classroom PM levels?
This one?
Yeah, this one. Looking at the left column, it looks like if you compare the indoor-outdoor, the particle, ultrafine particle, still compared to the outdoor, still factor of 2. And you mentioned the terpene and the teacher-student cooking pancake. What else indoor?
Yeah. So
particle source.
Indoors during I think we had a total of 18 days of monitoring from observational periods here. We did not see any evidence that terpene ozone chemistry influenced indoor levels during the time when students were present in the classroom at any of these sites. So that's the left-hand bar would not have included that contribution to source. The episode that I showed you of the pancake cooking is reflected in the data reported in S1, but because it's such a brief episode compared to about 10 hours of total monitoring, it elevates the level by 5 or 10%, but it doesn't change the qualitative picture. The other sources that we observed in the classroom, celebration of a birthday and a brief candle burning excursion from that, and then the operation of a heater for the first time in the season. And I don't think it's a combustion-related source in that case. I suspect it's just semi-volatiles associated with dust that had accumulated on the heat exchangers that are being boiled off and are forming ultrafine particles. But these, in sum, contributed very little to the total burden of ultrafine particles indoors at these 6 sites. So I would hazard a guess that 90 to 95% of what's reported for students in classroom indoor levels is attributable to outdoor particles intruding into the space.
Okay. And also the exposure, and you mentioned the student has the longer the duration time than teachers.
No, I'm sorry. If I said that, I misspoke. Teachers longer than students.
Longer, okay.
And you can see the summary here. The teacher's exposure is 80, and the student's is 50. And mainly, that's because of the longer duration of time that the teachers are present.
Right, that's not my question. And when you calculate the exposure, have you considered the children and the adults, the breathing rate is different?
Yeah, no, this is not an intake estimate.
Okay.
So it's exposure in the, as defined as the product of a time average concentration. And we used stationary monitoring, of course, in the classroom and assume that that's representative of the average in the classroom, multiplied by the duration of contact time. So the number of particles inhaled, of course, would be somewhat higher for the teachers because they are breathing at a higher volumetric rate than the students. The intake per body weight will be higher, or the exposure per body weight would be higher per unit exposure for the students because they breathe more air per body mass. But that is not incorporated in our analysis.
Okay. So it's not really the intake?
It's not intake, it's exposure. So if you think about the sequence of events, you have emissions, transformations, concentrations, exposure, the contact between the human and the pollutant in the space, then intake, dose, health effects, and so forth. We stop at exposure. Oh, you're going to go back to the
Yeah,
web.
I'll do a few more questions that were emailed in, and then we'll go back to the audience. Are you able to calculate the deposition rates of UFP? You provided some air exchange rates, such as in House 6 and some of the schools, and some combined air exchange and deposition rates, but no direct estimates of the deposition rates themselves. If you have a number in mind, could you also compare it with the PM 2.5 deposition rates, for example, 0.39 per hour, I believe it says, in the P team, and comment on any differences in the rates?
Okay, that's a astute question. Who wrote that? You don't have to tell me. Okay, so here's a summary of loss rates associated with the source activities. We have the best data on loss rates when there was an episodic release and a subsequent decay. And I don't have reported here, and I don't have perfectly in my memory, but I have an approximation in my memory of what the air exchange rates were in the houses that we studied. So let's just say, for the sake of the discussion, and this bears confirmation by looking at our final report, that the average air exchange rate was about 0.5 per hour. That'd be typical for residences. So here you see numbers that are in the range of 1.1 to 2.2 as the total decay rate, which is the sum of removal by deposition, removal by filtration to the extent that it occurs, but I don't think that's an important factor in these data, and removal by air exchange. We subtract off the removal by air exchange, so remove a half per hour, and you'd have a decent estimate of the deposition-associated rate constants. So those for the electric stove might be 0.6, and for the clothes dryer up to 1.7. So the typical numbers look like they're in the range of 1 to 1.5 per hour for ultrafine particle or particle number concentration decay. Now, the other number that was quoted here, 0.39 for PM 2.5. It's quite well known that the deposition to indoor surfaces is a function of particle size, with a minimum in the accumulation mode between 0.1 and 1 micrometer, and higher values either for larger particles because of gravitational settling and impaction, or for smaller particles because of their diffusive, more effective diffusive motion through boundary layers and reaching surfaces. So I would say that the 1 to 1.5 per hour that we're obtaining for ultrafine particles here is at least broadly consistent with what one would anticipate given the PM 2.5 number of about 0.4 per hour.
Just obviously that wasn't my question, but just following on that.
You didn't BlackBerry it in?
No, not good enough at that. So you just talked about deposition rates. Are you talking about apples and apples? Are you talking about particle numbers and probably particle mass? 2.5 is probably particle mass.
Sure. So you know, if you represent the size distribution in a self-consistent manner, either by number or by mass, then there's a deposition velocity that would apply for each particle size, and that would apply in the same way whether we were using a mass-weighted or a number-weighted distribution at each size. But I think this is the essence of the question that you raise. If we're looking at a number-weighted distribution as we are with UFP, then we're going to be really tilted towards the very small particles. And if we're doing a mass-weighted distribution, it's going to be, you know, I don't know where the center of that's going to be for indoor environments, but you'll have some contribution from 0.1 and some contribution from 1 micron particles, and you know, maybe some stuff in between. I think the critical issue is the question of how, strictly speaking, this shouldn't also follow first-order decay behavior. If you have a polydisperse aerosol and each of the sizes separately follow first-order decay, but they have different rate constants as we expect, then the small particles will disappear more rapidly and the decay will slow over time. I'm what's the word, dissembling. I think the story would look coherent if the particle number concentration is dominated not by particles that are 10 nanometers, but maybe by particles that are 50 nanometers in the indoor environment. And then this story would be roughly consistent. And if it was really 10 nanometer particles, I would expect higher deposition rates than what we're seeing here. They're bigger particles.
Yeah, for the residential cooking episodes, Was there any record made of, the different types of food that were being cooked during that?
Yes,
Oh, there was.
we do have a
Okay.
record, but it's, it's kind of this. There's a little bit more than this. So, you can see A here. This is for H6. I mean, I have this kind of data for each of the sites, but not on a visual. The stove was used, and I think we have what they were doing with the stove. Boiling water, and they were operating a rice cooker at the same time. The frying, I know what kind of food they were cooking when they were frying, but I don't know how many people they were trying to serve or what exactly the style of cooking was in detail. The GF grills, George Foreman grills, so they're like barbecuing some burgers indoors or something like that. I don't know. So it was just observational, and you can imagine all the different ways that people cook.
For sure.
And that we didn't characterize the cooking episodes very precisely. When we did manipulation experiments, we did some cooking-related manipulation experiments, and they were kind of precisely conducted in terms of exactly how much we cooked and for how long and what type of food and so forth. But frankly, I don't think they inform us as much about what's really going on in households as this observational monitoring does, as uncontrolled as it is.
Right. Okay. Thank you.
Another question that was emailed. Did ventilation over the stove influence the PN measurements in the rest of the house, such as did the use of a good hood over the stove reduce concentrations?
Okay, so that's a great question, and we have some data that we did not, to be honest, scrutinize in great detail. That is, what I don't know is that at every site did we have religious recording of whether the range hood was on or off with each cooking episode. It is noted at some times with in association with the indoor activity log. And what I can tell you is that even in cases where it is noted, we see particle levels that don't look systematically different, at least to first glance. So I don't think the quality of the data that we have would allow one to draw any kind of firm quantitative inference. I know from work that was done a long time ago that range hoods in their efficiency were only kind of 50, 60, 70% effective in capturing the exhaust from the plume, and stuff would spill out over the edge. And given the high degree of variability associated with cooking activities, you could imagine then that, we would still see particles coming from cooking episodes even when the range hood is operated, and we would still see a lot of particles, even if only 30% of what was emitted got into the general space. It's not a very precise response to that question, but maybe that's the best I can do with the evidence that we have.
Another question. You haven't mentioned residential wood burning as a source of PM. Do you have an opinion about what you would find if you also looked in homes, for example, wood stoves?
Wow, you have some great folks on the web. My expectation, first, there is no evidence, and I'm pretty sure there was none, of wood burning in the households that we monitored during the observational period here. In the event that wood burning took place, whether in wood stoves or in fireplaces, my expectation is that there would be some spillage of we know burning wood will generate lots of ultrafine particles, and I expect that from other studies, not looking at ultrafine particles, but looking at other pollutants associated with wood combustion, that there will be some spillage of the generated pollutants from wood burning that get into the house. How much that would contribute relative to the things that we've observed here, I don't have a basis to speculate at all reliably. The speculation would be wild, and so I'd rather not.
how can you be sure that the measured values outdoors, especially in the residential areas, that the sources for those were independent of indoor sources?
You know, I think the only point that, I don't know that for sure, but when I look at signals like this, that interpretation just doesn't suggest itself, because the possibility that what I'm observing or monitoring here outdoors was significantly influenced by the presence of the indoor particles, at least from this site. Now, I guess it's not out of the question that some other neighboring sites might have been the source of what we were observing there. We did see, you note at about 22 hours here, this interesting kind of big excursion in the outdoor particle level. I think that's real. It's not just 1 minute, several minutes duration that sort of rises and falls. And we had a few occurrences like this that I'm fairly confident are associated with neighborhood proximate sources rather than with kind of more regional stuff. But we don't know exactly what. So, you know, conceivably, H6 was like in the summertime, so it's not a cooking, I mean, it could be cooking. It's not a wood burning activity that would have.
Thinking of times when I've walked down the street, let's say during the summer, around 4 to 6 p.m., and somebody's cooking something, and it's wonderful, you know?
Yeah, well, you know, if that was significant, I would expect to see some echo in the upper trace of what we are seeing in the indoor trace here. And I don't see that at all in these data.
And in general, I see what you're saying there, but it seems like it's possible that, let's say somebody opens their window for an hour and they're cooking something and then they close their window, or you know, things like that could happen. And how far away were the monitors, outdoor monitors, from the residences?
Well, look, you know, it was like, we weren't so focused on that question. We were focused on the reverse question, which was to try to make sure that what we measured outdoors was relevant to what was getting indoors from outdoors. So we tried to place them as close as possible. At this particular site, it was immediately adjacent. You can see its positioning against the outdoor wall. Mm-hmm. And so, yeah, it's not inconceivable that the neighbor, or, you know, the neighbor would have been asynchronous with the emissions here indoors, that the neighbor might have influenced this level. I can't rule that out. I don't think it's a big factor, but I can't rule it out. Eileen?
Related question would be then, did you control for open windows? Did you let the people just open the windows as they typically do? And what was your sense? Were typical windows, you know, generally closed, or?
So I didn't really speak to this, but we did pay a lot of attention to that issue. And the way that we paid attention to it was questionnaires that we had like 3 different types of questionnaires. There were things that we asked the occupants to fill out that were daily diaries that included building configuration questions, but also source-related activities. You know, were you cooking, and when people were home and not home. We tried to make them as simple as possible so they weren't, you know, we didn't get any fatigue from the residents. And then we would have daily visits by our field staff to download the data from the instruments, and they would check in with the occupants to make sure that the previous day's diary had been filled in. And at the beginning of the monitoring period, they would do a walkthrough to take the dimensions and ask questions, and make observations and ask questions of the occupants then about their typical behaviors related to things like window opening. So in addition to that sort of kind of informational questionnaire-based evidence, we had some hobo-based proximity sensors and temperature sensors connected to data loggers, these small portable units. And so we would deploy 3 or 4 of these on the doors, front and back door, to monitor when people were coming in and going out. And then on a couple of windows that the occupants reported were the ones that they typically would leave open. So we have this evidence. When we measured air exchange rates, we attempted to do it using when it was appropriate, the two dominant configurations that applied for most of the period. So if people had their windows open sort of part of the time, and we had a record of that, then we would make an air exchange rate measurement by tracer decay under those conditions. And then we would do another one with the place closed. I have the sort of numbers that we recorded from this. It didn't look too promising to try to extract dynamic modeling or to try to apply a dynamic model that looked into how air exchange rate might vary as a function of time as an important factor quantitatively in these features, except maybe in the way that I described it for schools, where there was a very strong influence of the difference between when the school is unoccupied, the room's closed, and the classroom's running at a half an air change an hour or 1 air change per hour. And then the kids are there, and it's the afternoon, and it's starting to warm up, and it's getting stuffy in the classroom. And so the teacher throws open the windows, throws open the doors, and all of a sudden we're at 5 air changes an hour, and it's an entirely different case.
It sounds then like in homes you're not seeing that sort of
dominant change, yes.
You know, case where a lot of windows are regularly open.
Right.
And that's what I was sort of wondering about. Because, for example, here in Sacramento, I know I and some other people, when the Delta breeze comes up, you tend to open all the windows to cool off the house.
Right, and so we only were monitoring almost all of our houses were on the other side of the hills of the East Bay, so they get the Oakland and Emeryville, they get the cooler days anyway, even when we're monitoring in the summer. The one house that we monitored on the east side of the hills was in Livermore. That happened to be at the tail end of the huge forest fire problem that we had in Northern California in 2008, the summer of 2008. And actually, the outdoor ultrafine particle levels during that time were they're remarkably low. And I think they're low because the very heavy loading of PM 2.5 from the forest fires acts as a coagulation sink and prevents any nucleation from occurring as well, because it scavenges semi-volatiles. And so the lowest outdoor UFP levels that we measured were during this monitoring in Livermore. They had air conditioning, so they didn't leave the windows thrown open either.
Right. Very nice presentation. Thank you. Very interesting. My question has to do with vertical gradients, and I'm trying to recall, I don't believe you measured any vertical gradient, say, in a home. But if you did, or even if you didn't, if you're aware of any literatures or any literature information you have on vertical gradients, my question is stemming from your findings that the in-home exposure appears to be more significant than, say, at the schools, and I'm wondering about the rugrats, the kids down low, would they be getting greater or lesser exposures, or do we not know that yet?
Okay, so there's a few points that I should make. At some, the enclosures were fixed configuration. They were always monitoring from 1.5 meters above ground level. So we didn't look within a room at vertical concentration fields. We did, and this house is an illustration of it, do upstairs and downstairs monitoring. And something I didn't point out, but is, I think, evident here. Let's see, the upstairs one is called enclosure 1, and the downstairs one is enclosure 3. No, that's enclosure 3, sorry, is upstairs, and enclosure 1 is downstairs. And you see where the kitchen is located here in the downstairs area. So note that the lower trace is actually from monitoring upstairs, and the middle trace is from monitoring downstairs. And note the scale here, that the upstairs particle levels during cooking episodes were actually considerably higher than the downstairs levels. And I think that's a thermal plume issue. So you cook, you generate a huge amount of heat, the ultrafine particles and the thermal plume rises, and if there's an open upstairs, it continues rising before it starts coming down to and mixing throughout the first floor. So from that point of view, I think there is sort of a question to raise. That is, what role might thermal gradients play in influencing the spatial distribution of concentrations? But I know from other studies of indoor airflow that the story gets pretty complicated. You get, in general, along warm walls, the air rises, and then it sort of flows across the ceiling, and then if there's a cold wall or a cold window, you'll get a flow along that, and it'll sweep along the floor. So if you had high levels at the ceiling, you might actually have high levels at the floor then, because of this airflow pattern, before you get high levels in the middle of the room. I can't do that. My expectation is that those are likely to be secondary influences of secondary importance for ultrafine particles. That's different than the story that I would expect if we were thinking about particle resuspension from flooring as an important source, like pesticide-associated dust or phthalates that are in the dust that get resuspended. Then, I think children's activity on the floor might be really important in terms of influencing their exposure. In this case, because the floor is not likely to be a source, at least not a strong source, and the ultrafine particles just behave like big gas molecules anyway. I think the idea that things are pretty well mixed is probably a good working hypothesis.
Great, thank you. And then one quick comment related to cooking. We do have a final report on our website from a cooking study we funded a few years ago that Arcadis did for us, and they looked primarily at the PM 2.5 and 10, but I think there was one monitor, and I can't remember what we used or what the investigators used, but I think there is a little bit of UFP data from that study, and I think it's in the report, or if not, I can look at that. But I think we do have a little bit of data previously from all the different, they detailed very carefully what foods and how long they were cooked. They did both gas and electric stoves. I think in answer to some of the
Okay.
comments.
Well, there's also a considerable amount of data collected mainly by Lance Wallace and some of his co-conspirators. The Lance Wallace townhouse study, 2 years of unbelievably detailed monitoring in one house. So we know absolutely everything about the particle levels at that home, including what tortilla surprise looks like in terms of producing particle size distributions on Friday night.
I have 3 more questions that were emailed. What is the toxicity of cooking particles compared to outdoor particles?
Unknown.
You showed that increased ventilation rates in school classrooms was associated with higher PN. This is opposite to the expectation on ventilation rates for the levels of VOCs, such as benzene, intruding into indoor air from soil and groundwater contaminants. Could you discuss this effect of ventilation rates on expected levels of PN versus VOCs in indoor air in schools? Any recommendations?
Yeah, that's also a really insightful question. So I think the story in schools has this two-edged sword. You ventilate better, and you do a better job of bringing outdoor pollutants into the classroom. And if those pollutants have dynamic removal processes, then that means higher exposures. But you ventilate better, and you do a better job at diluting not only the emissions from things like groundwater contamination that may intrude, but emissions that take place from activities within the classroom itself, or the furnishings within the classroom. If I had enough money and the power of the king, I would suggest that the way to wrestle with this problem is ventilate and mitigate. And how do you mitigate? You mitigate at 2 levels. One is you pay attention to indoor emission sources to make sure that none of those are excessive. You keep those down to a minimum. But I think you also pay attention to outdoor pollution levels. So mitigation, we know how to filter particles out of air economically, effectively, and we could do that in schools. We know how to filter ozone out of air economically, I would argue, relative to the health significance, although that probably bears more careful study, and reliably using activated carbon. And so we could have high quality ventilation systems in schools that did a good job filtering particles, did a good job filtering ozone from the outdoor air, did a good job with ensuring that any indoor emission sources were not excessive by attention to those sources, and provided enough ventilation for it to be a good, productive place for children to study. If I were king.
Are there any more questions from our audience? Okay. The last question is just if the presentation and or final report are available on the web.
The presentation slides are certainly available, and you know better than I how to find them, but I found them by Googling chairs seminar series and then looking for my name. And I was able to download them, so anybody else could, I suppose, as well. As far as the final report, I think that's up to the agency. You have it. Good.
So yes, the presentation slides should be available through our website, through the link that gets you to the chair seminar series, and then the final report will be posted online sometime in the near future, but I can't tell you exactly what date. So with that, I'd like to conclude our chair seminar series. I'd like to thank William Nazaroff for presenting today, and for our audience attending and watching on the web. Thank you.
Thank you.